Today we are going to talk about chemistry. So chemistry apparently is, I think, one of the biggest chapter that you have to handle in ANP 1 course. But we can divide that into two parts: chemistry part 1, chemistry part 2. Chemistry part 1, we talk about like simple things like matter, atoms, molecules, compounds, different type of bonding, a little bit of acid base, pH, etc. And chemistry part 2 basically talk about organic chemistry. So we're going to learn more about carbohydrate, protein, lipid, and nucleic acid. So together, this is chemistry chapter. So first we are going to, today we are actually, this particular lecture, we're going to learn about the first part. So let me get the PowerPoint slide for this. So as I said, the first part, first let me explain what I expect you to know from this chapter. This is not a chemistry class. This is an anatomy and physiology class. So those who already have taken some chemistry class, for you guys, it's going to be very easy. And those who have not, I would try to make it as simple as it is possible, meaning we are going to learn as much as required for this class. So what we are going to learn, so please take a note of that. So we are going to learn about matter, we are going to learn about elements, compounds, atoms, a little bit of detailed chemistry of atoms, meaning atomic number, mass number, isotopes. Then we are going to learn about different type of bonding, ionic bond, covalent bond, hydrogen bond. Then we are going to learn about a little bit of water properties. And then we are going to focus on acid, base, and the pH scale, and a little bit of solution, and then the definition of reactions and some different type of reactions. So not in this particular order, obviously, but these are the material that we are going to learn in this chapter. Okay, so let's start with the simple thing called matter. So matter is what exists. So whatever things that exist we call matter. So obviously all living things, including human body, is consist of matter because we do exist. Okay? So matter that occupies some space. So now, how they occupied? They can be either solid, they can be either liquid, or they can be either gas. So solid, basically that has a definite shape and volume, in which cases the unit, I'm going to name it later on, the unit that makes the matter, those each unit are close by. In liquid, they have a definite volume, but obviously they take the shape of the container. So if you pour water in a glass, it will take the shape of a glass. If you put that in a bowl, it will take the shape of a bowl. So they don't have a particular or definite shape, but they do have a definite volume. So the liquid, the unit which makes that liquid a little bit far apart compared to the gas. So if the gas, the units are here, the liquid units are going to be far apart. Then come gas. Gas has both their volume and the shape can be changed. So if you take, let's say, 100 ml gas, and if you put them into a small 1 ml vial, it's going to fit. So their volume and shape both can be changed. Okay. One more time, the unit that making this matter in the solid, they're very close to each other. They're like clumped together. In gas, they're in liquid, they're slightly apart, and in gas, they're far apart. Okay. Now, those units, the most the basic one, the fundamental one, is called elements. Okay, it's called elements. Now, so what is an element? So element is a pure substrate. that substance cannot be broken down into simpler substance. What does that mean? That means if you just, I'll give you a very simple example. If you take a gold bar, so let's say this is a gold bar. So if I take a gold bar and if I break into half, I will have two gold bar. And then if I keep breaking that, one point of time, you will reach all the powder of gold, but they're all gold. Now, even in your head, if you break them down more, this is how I understand it. So make sure you do understand this, and it'll be easy for you to think. So even if you in your head you go to break down more, one point of time will come when you break that gold one more time, it's not going to have the properties of gold. Same is true for, let's say, iron. If you take an iron rod and if you keep breaking that one time, you will reach all the powders of iron. They will have the same properties of iron. They will be still attracted by a magnet because we know a magnet attracts iron. But then one point of time, if you keep breaking, even in your head, in your mind, one point of time, once you break that tiny, tiny, tiny iron particle, those are not going to be attracted by magnet because they are not iron anymore. So that last one, same as gold or iron, the last one, once you break one more time, it's not having a property of gold or iron. The last one is called atoms. So atoms are the basic fundamental unit of an element or any substance. So what is an element? In an element, when all the atoms are identical, that means so-called pure substance. If you take water, if you keep breaking, you are going to have two elements there, hydrogen and oxygen, because when you come to the atomic population, you will have two types of population of atom. One is a hydrogen atom, one is will be the other population will be oxygen atom, because remember water is H2O, meaning two hydrogen with respect to one oxygen. So they will have, let's say, 100 billion of hydrogen and 50 billion of oxygen atoms in a drop of molecules. I just made up that number. So element where all the unit that we just discussed, which are called atoms, are identical. And in case of a compound, which is what water is, all the atoms are not identical. They can have two or more various type of atoms. So normally elements we call like the basic unit we call like atoms. And then it can, and so element, imagine one more time. So I have a, let's say, gold on my left hand mirror image, okay? On the other hand, we have, let's say, iron. And if we keep breaking them, one time it will reach that both are atoms of gold and atoms of iron. If I break them, what do we get? We get subatomic particles. Subatomic particles. Subatomic particles, many of them, we're going to focus only on three: proton, neutron, and electron. So once we break open an atom, we get proton, neutron, and electron. Proton is positively charged. Electron is negatively charged particle. Neutron is neutral. They have no charge. So proton and electron, they're oppositely charged, but they are equal strength of charge. What does that mean? Now I quoted that word strength. What does that mean? That means once you mix one proton and one electron, they will neutralize. So they will become a zero or neutral charge. And as far as their mass is concerned, proton, we consider they have mass. Neutron, we consider they also do have mass. An electron is not massless, but for all practical purpose, we ignore their mass because proton is already a very tiny thing. And one electron is one, like 1836 electron together makes a proton. So it's like 1/2000 almost of that weight. So for any calculation purpose, we ignore the mass of electron. But you consider the mass of proton and the mass of neutron when you discuss about the mass of an atom. So you're coming that later on. Before we go there, there are a simple couple of information that you need to know is in nature, in the earth crust in nature, there are lots of elements, meaning pure substance, such as I mentioned, like hydrogen, oxygen, gold, iron, bromine, chlorine, iodine, etc. Different book use a couple of different numbers, but your textbook will use 92. So we are going to that number, 92 different elements that occur naturally on Earth. But there are some artificial more that scientists already prepared in the in the laboratory. So we have more elements in the periodic table. Those who have a chemistry background, they know we arrange all the elements according to their atomic number in the periodic table. But we don't have to memorize all 92. Okay, we have to memorize few of them. But how do we define them? Normally, they are identified with the symbol. They most comes from their English names, either one letter or two letter symbols. For example, hydrogen stands with H, carbon symbol is C, nitrogen N, oxygen O, and some they come from the Latin word also. For example, sodium Na, which is a Latin word called natrium, or potassium K, which is no K are here, but potassium K because it came from a Latin word called kalium, or iron, Fe, that's a Latin word called ferrum. So some of them and most of them come from the English literature. Okay, again, you do not need to memorize any of the symbols. So in the exam, I am not going to ask question, what is the symbol of magnesium? Or what is the symbol of phosphorus? I'm not going to ask those questions, but excuse me. But if you do know these, particularly that mentioned in this slide, it's helpful for your future reading. So when you read the book, when you read the notes later on, these are the ones that are going to be used frequently. So it is helpful to know them. Okay, again, do not need to memorize them, but I'm almost 100% sure that you guys know these. Just take a reading a couple of times. Okay, so these are symbols. Now, two important things. One is atomic number, two is mass number of an atom. So first, let's learn the definition. Atomic number is the number of proton. I intentionally coming to that slide later on. Okay, atomic number is the number of proton in an atom. And mass number is the total number of proton and neutron in an atom. These are the two simple definitions. One more time. Atomic number is the number of proton in an atom. Mass number is the number of proton and neutron in an atom. Because different atom has different number of proton, different number of electron, different number of neutron. So those are the two definitions. You must know it. Detail coming up. Before we go there, how about human body? We have 92 naturally occurring elements. So how many we have in human body? Human body has approximately 24 to 26. There's always a debate in different books, number of naturally occurring elements in the body. Out of that, some book will say 4, some book will say 6 of them are significant, meaning we call them major elements. So those are oxygen, carbon, hydrogen, nitrogen. So oxygen, carbon, hydrogen, nitrogen, these are the 4 major elements. Most book will say that. Some book will also consider calcium and phosphorus into that. Okay, so for our purpose, we're going to focus on these 4. Carbon, oxygen, hydrogen, and nitrogen. These 4 are the major elements, and then come some, these 4 are the main elements, I would say. And then come major group include, let's say, calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium. You don't have to memorize them. And then there's something which is a very tiny amount. Those are called trace elements. Again, you don't need to memorize these as well. But here's the one very important thing I want you to understand it. trace elements, meaning we have less than 0.01% of our body weight, but that does not mean we don't need them. For example, if we don't have iron, we are not going to make blood in the body, for one thing. There are several other things you will not be able to do it. If you don't have iodine, your thyroid gland will not be able to produce thyroid hormone, and so on. So all these are essential, meaning you are going to need them for one reason or other, but they have less quantity. Again, you just need to memorize oxygen, carbon, hydrogen, nitrogen. These are the 4 main components, and the rest right here are all they are required by the human body. So before we go to the atomic structure, I want you to know this first. Okay. So atomic number of an atom is the number of protons they have. Atomic number of an atom. Now, we arrange the periodic table is arranged according to the atomic number, to the height. Now, here is a very important statement. In an atom, the number of protons and the number of electrons are identical. So what does that mean? That means if an atom has 10 protons, they also do have 10 electrons, because atoms are electrically neutral. So when we're defining atomic number, we're defining according to the number of protons. We are not defining them according to the number of electrons. The reason is simple, because an atom may gain or lose electron. The atom may gain or lose electron, but they don't gain or lose proton, because once they do, they change themselves, meaning they are not the same atom anymore. So atomic number, although number of proton and electron are equal in an atom, but atomic number is defined as number of protons. But if it says that carbon has a 6 proton, that means carbon atomic number is 6. Therefore, carbon also do have 6 electrons. Oxygen, their atomic number is 8, meaning they have 8 protons. Therefore, they also do have 8 electrons. Now, can oxygen accept more electrons? Yes, they can. We are going to learn that later on. Mass number is the number of proton and number of neutron together. So whatever number they have in protons and the number of neutrons together, that's called mass number. As the reason is, as I said earlier, without going into very detailed chemistry, that electron, they are so light compared to even a proton is like almost 1/1800th. So we ignore their masses. So when you consider the mass of an atom, we look for proton and neutron together. This is how we write down. Normally, this is not an approximately, like I tried in Microsoft's Words, and the slide that didn't gave me that opportunity to do exactly what I wanted to do. But this is how we write. We write on the superscript the mass number, and on the bottom, like the subscript, the atomic number. So if an atom, their formula is symbol is X, their atomic number is written here, mass number written here. This is a convention. Okay, so mass number is proton and neutron together. Atomic number is number of proton. So if I give you a mass number and an atomic number, you should be able to tell in that atom how many protons they have, how many electrons they have, and how many neutrons they have. How? Because if the atomic number is 6, they have 6 protons, and they also have 6 electrons, because their numbers are same. And if the atomic number is 6 and the mass number, let's say 13, so 13 minus 6, so 7 will be their neutron number. Okay, that is how you can easily calculate those two from mass number and atomic number. Now when scientists studying in the nature, let's say they are looking at carbon. In the nature, they found an amazing fact. They found that the carbon, naturally occurring carbon, I'm going to say the number, the mass number is 12 and atomic number is 6, okay, normally. But when scientists look into detail, they found not only one, there are multiple variety of carbon. Same is true for every single other elements they looked into. So what is that variety? So let's look at the carbon. So when they looked at it, they found this is a naturally occurring. Most carbons are like that. They have 12 mass number and 6 atomic number. But they also found 13 mass number and 6 atomic number. And they also found 14 mass number and 6 atomic number. And what does that indicate? That indicate that means in nature, we have multiple variety of carbon, same element. Their chemical properties are same, their physical properties are slightly different. Physical property, particularly in this case, their mass is different. They are heavier. We call them simply heavier atoms. And together, their relationship, we call them isotopes. So isotopes of carbon means different one of them with a different neutron number because their mass number is different, but their atomic number is same. So the proton is same, only difference is their neutron number. So isotopes, they're different with their neutron numbers. So different number of neutrons, different isotopes. Again, as I said, in nature, there are plenty of them. Now, one interesting part about isotopes. What isotopes are, like these, say for example, this 13 carbon or 14 carbon, that is how we refer to them, or heavy carbon. Same thing with hydrogen, we call heavy hydrogen, nitrogen, we call heavy nitrogen, oxygen, heavy oxygen. All these isotopes, they're not stable. They're not chemically stable. So all of these, they want to get to here or any other stable form. Like the detailed chemistry, we don't need it, right? Just think this way, simple, that these isotopes, their radiation is less. Let's say in 100% carbon, this will cover up like 98% or maybe 99%. I don't recall the exact number, close to that probably. And so these are very little. But they're not stable. They want continuously, these are continuously changing to a stable form. When they change, what they do, this is what interesting. Okay, when they change, what they do, they radiate energy. That's why these isotopes are always also called radioisotopes. So because they radiate energy, all the isotopes, they radiate energy because they want to get to the stable form. They radiate energy, they get rid of the energy particle, they want to go to the stable form. Now here's the interesting part. All radioactive does not mean always bad, meaning all radiations are not that harmful. There are some radiation, commonly called ionizing radiation, they are harmful, such as in X-rays. So X-ray, they have a lot of high energy particles. They are harmful for your body. But all radiation, for example, in your body, you have carbon, you have potassium, and some of them are radioactive. Like some of those isotopes are radioactive. Yes, they are radiating energy, but they're not harmful because their energy they have a very low energy radiation. But some of them, they have a very high energy. Those could be harmful. Okay. So the reason I'm discussing this, I want to mention one more thing, because some of these radioisotopes can be useful for medical study or medical imaging study. Particularly, this example will define exactly what I meant to say. For example, iodine is the molecule or is the element that can be utilized by thyroid gland. Thyroid gland is right here, right in this case. Okay. So thyroid gland, they take up iodine from blood. Okay. Now iodine has a different number of isotopes. So this number define that what isotopes you're talking about. These are like iodine 123, for example. So some isotopes are a little bit dangerous, some are not. So this is not so much. So what happens is when you give the patient that particular iodine in their body, let's say in their blood, when the iodine goes, they're going to be accumulated in the thyroid gland. Because as I said earlier, thyroid is the only tissue that, only gland that accepts those iodine. So when iodine accumulate, because they are radioactive isotopes, they are going to radiate energy. And those, without going into very detail, those energy can be scanned by a scanner outside of your body. And they can give you this kind of computer imaging. And looking at those images, doctors can literally figure out like what is the condition of a thyroid gland. That's one way of studying. Another way of similar, let's say that somebody has a Graves' disease or Hashimoto's disease, they got or something cancerous problem in the thyroid gland, so doctors surgically remove, but it is not sometimes possible to remove every single cell of thyroid gland because they don't want to damage the other organs or other gland nearby. So some of them are left. Then they can use a higher, like iodine, for example, 131, that's a little bit higher, I would call it higher energy isotopes. And those isotopes, when they accumulated in those remaining tissue, they radiate energy which can destroy that tissue or destroy the cell, because that is what doctor wants. They want to destroy those cancerous or defective cells anywhere. So there are a lot of use of these isotopes in the medical field. Excuse me. So let's go back to this particular part where atomic structure. So how an atom look like? This is atomic structure, means how an atom looks like. So there are obviously different theories exist. One is called like their cloud structure or wave nature structure. The other one is simply like solar system model. So we are going to use this particular model, like a solar system model, to understand them very easily, simply because in ANP we do not need that detailed structure anyway. So what is the solar system model? Exactly like solar system, the sun is in the middle somewhere and the planets are revolving around the sun. Same thing here. The nucleus is at the center. So what is nucleus? So atoms nucleus, they consist of all their proton and all their neutron. So whatever number of proton and neutron they have together combined, they are in the nucleus. So they are all located at the nucleus, and electrons, they're rotating around them like planet revolving around sun. So electrons are revolving around this orbit. We call them literally orbit or shell. So electrons are going from this, going around, revolving around the shell, and that's the structure of an atom. So all their positively charged proton and neutrons are right here, and negatively charged electrons are revolving around the shell, around the nucleus or to the cell. Sure. So how many shells we have? Do we have one or more? That's what we're going to discuss. So this example, this is showing you we have obviously more than one. So we have approximately like 7 shells which can fit all the naturally occurring elements so far we know into that shell. Okay. So now here's the important part. This, where the nucleus is, ignore the word carbon. I don't care about that right now. So this is the nucleus, all their protons and neutrons. This is the shell. So this is the closest shell from the nucleus. This is shell number 1 or orbit number 1. That's orbit number 2, then orbit number 3, orbit number 4, and so on. So the 1, 2, 3, 4, that's how we name, or we name them as like a K, L, M, N, O, P. That's what we name. Or this is simply called like first shell, second shell, third shell. Now, the second point is very important. The farthest the shell is, so from nucleus, the farthest the shell is, that's a higher energy electron is there. So electron always try to accumulate this lower one, but if they can, they go to the higher. So the energy is high, more you go towards the outermost shell. So the electrons are here on those shells. Now, how they are distributed, that's very important to know, how they're distributed. So they are distributed in a pattern. So the first shell, these are the two things very important. The first shell will have the electron first, meaning if an atomic number, let's say in this case 6, that means they have 6 electrons. So the first electrons must be on the first shell. And then how many? The question is. So the electron, they must occupy the closer to the nucleus shell first, and then they go out. That's number one theory. And number two is there is a maximum number of electron can stay in a shell. And that is given by a formula called 2n square. I think I have a slide right after this. Use this one. Okay. By the way, this one we already discussed. That's why I'm just moving to this particular slide. So the maximum number of electron in a shell is given by the formula 2n square. N is the number of shell. What does that mean? So the first shell, the n is 1, because that's a first cell, number 1 cell. So 2 times 1 square is, oh, sorry about that. That should be 2. So this is a mistake in the slide. So 2 times 1 squared should be 2. Similarly, 2 times 2 squared should be 8, like 2 times 2, 4, and then 4 times 2, 8. 2 times 3 squared is 18. So the first cell, again, make sure you correct that slide. The first cell has 2 electron maximum. The second cell can have 8 electrons maximum. The third cell can have 18 electron maximums. This is how we fill the electron. But here's the important part. The first cell must completely filled before electron goes to the second shell. Same is true for second cell. Second cell completely filled before it goes to the third cell, and so on. But again, right here, those who have a little bit detailed chemistry background, they already know that there is some discrepancy among the third and fourth and fifth and so on. We are not going there. Okay, we are not going into the subcellular model, meaning subshell, meaning or orbital, like SPDF, probably those are going around your head right now. We don't need it for A and P. Okay, so SPDF, that detail, you do not need to study at all. And I believe your book does not also have that. Okay, so we are going to focus only in this. That's good enough. This arrangement called electronic configuration, I'll give you 2 easy examples. Sodium has 11 electrons. So total number of their atomic number is 11. So they have 11 protons, therefore they have 11 electrons. Now out of these 11 electrons, so 2 will go into the first shell. That's how we write, comma 8. That's the second shell, because second shell cannot have more than 8. Then the last electron will go to the third shell. Okay. Same thing, chlorine. They have 17 electrons. So 2 must go to the first, then 8 go to the second, so 8 plus 2, 10, the remaining 7 goes to the third, and so on. That's how we write electronic configuration. So now when scientists are discussing about all these things, they're studying this, they found an amazing fact. This is important. What they found is when an atom, they have 8 electrons on the outermost shell, they are extremely stable. One more time. When an atom has 8 electrons in the outermost shell, they are extremely stable. Now, first thing, what is outermost shell? So right here, the sodium has 281. So that's their outermost shell, because that's the first shell, that's the second shell, that's the third one. So that's the outermost shell. In chlorine, same thing. Number 3 is the outermost shell. But if we go back right here in carbon, the second shell is the outermost shell, because their electronic configuration is 2, 4. So these 4 electrons in the outermost shell. In hydrogen, the number 1 shell is the outermost shell, and so on. So when we come to that, again, that rule that I was discussing, that when the scientists found that once they have 8 electrons on the outermost shell, they're extremely stable. And those are like all the inert gases or noble gases. They're chemically very stable, like helium, neon, argon, xenon, krypton. Those are extremely stable gases. That's why they are called inert gas or noble gas. They don't react with another. And interestingly, in chemistry, all chemicals, they want to reach that state. Everybody wants to get stable. Like even in this crazy situation, we are all studying because we want to be stable. Because in life, everybody wants to get stable. Same thing with chemistry. The atoms wants to get stable. How they do it? Once they have 8. There is an exception for lower number. The 2 is also stable because they follow the helium structure. So let's focus on 8 right now, because that's sometimes also referred to as the octet rule, because number 8. Okay. So now the question is, how can sodium be 8 at the outermost shell? This is the outermost shell. So what they can do, they can accept 7 more electron right here. So if they accept 7 more electron, they become 288. They're stable. Or there is another way, they can lose this electron. So if they lose this electron, they become 28. Now 8, the second become their outermost shell, and they are stable. So sodium can reach to that stability 2 ways. 1, they can gain 7 electrons, or 2, they can lose 1 electron. So obviously gaining and losing in chemistry both require a lot of energy here. So gaining 7 is too much of a job compared to losing 1, so they will prefer to lose 1. Now if you look at chlorine on the other hand, same thing, they can lose the 7 electrons, then they become 28, or they can accept 1, they become 288, still 8 on the outermost shell. Obviously, again, the same reason, they will prefer to gain 1 rather than losing 7, because losing 7 is 7 times more works. Now here in chemistry, interestingly, in real life, if you want to lose something, let's say you want to lose this pen, you just drop somewhere, forget someplace, and you will lose it. But chemistry is not like that. They cannot lose an electron if there is no one willing to accept that. So sodium can lose the electron when there is somebody is willing to accept that. So that somebody could be chlorine. So when you put sodium and chlorine side by side, what will happen? Sodium will literally transfer 1 electron from their outermost shell to the chlorine. Sodium is happy because they wanted to lose 1. They're just looking for somebody to accept. Chlorine become happy because they want to gain 1. They got 1 for free. So now what happened? When sodium lost 1 electron, this is what interesting, and you have to understand this. I'm going to use this particular picture to explain. So sodium, their electronic configuration is 281 because they have 11 atomic number. So when they have 11 atomic number, they have 11 proton and 11 electron. So they're electrically neutral. Remember, proton positively charged, electron negatively charged, together they're neutral. So they're electrically neutral. Now they lost 1 electron. That electron is gone. So they have 3 shells. Now the last shell, we don't need it because there's only lone electron. They're losing it. So now the sodium has 10 electron, but 11 proton. Because proton, they didn't lose. They can't lose. So once they lose 1 electron, but they have 11 proton, so now 10 electron will nullify or the neutralize the charge of 10 proton, but 1 proton will remain stand. And that's a positively charged. That's why it's called Na+. So now we call them ion. We call sodium ion. Same thing with chlorine. Once chlorine gained the electron, they used to have 17 electron, 17 proton, neutralize each other. But now they have 18 electron, 1 electron extra. So they're showing off a negatively charged. Right here, negative charge. So now they are negatively charged ion. This is a positively charged ion. This is sodium ion, this is called chloride ion. And when the ion are positively charged, we call them cation. And when their ion is negatively charged, we call them anion. So cation, sodium is a cation because they are positively charged ion. That's just a name. And chlorine become an anion because it's a negatively charged ion. So this is what we wrote down detail about. Sodium is a positively charged called cation. Chlorine is negatively charged called anion. Now what happened? When a positively charged and a negative charge come side by side, they attract because we know opposite attracts. So the oppositely charged ion will attract together and that create a bond. That relationship is known as ionic bond. So ionic bond will, as a result of a transfer of an electron. So when electrons get transferred from one atom to another, the bond form is known as ionic bond. Okay. So there are two more other bonds that we are going to discuss called covalent bond and hydrogen bond. So what happens is sometimes in order to reach 8, the atoms, they cannot just get rid of or accept electron. What they do, they share electrons. So for example, just to understand this, for example, let's say carbon, on their outermost shell, they have 4 electrons. So how can they become 8? Or how can they become 2? As I said earlier, 2 could be also stable. So let's think about how can they become 8 first. So they can get another 4 electrons, then they'll become 8. But getting another 4 electrons is a lot of energy involved. So what they do rather, they will share with somebody else. So what they do, hydrogen, they always wanted to reach to 2 because they become the structure of a helium, which is also a noble gas, 2 outermost shell. So what they become right here, if you pay attention in this particular picture, there are 4 carbon, they have 4 electrons on the outermost shell, but hydrogen, they have 1. So they also technically, I'm just going to use this word, dump their electron on the same shell. So now carbon at a given moment, they have 8 electrons, so they are stable. And hydrogen at a given moment, they have 2 electrons on the outermost shell, they are stable. Same thing happened when 2 oxygen atoms combine together. Same thing happened when 2 hydrogen atoms combine together. So if they share, they're both happy. And that sharing of electron form the bond called covalent bond. So covalent bond is a result of sharing of an electron. Ionic bond is a result of transferring an electron. So there's a big difference between two. So this is called sharing of electron. But whenever there is a sharing, we know most of the time there is a problem because not everybody can share nicely. So let's say, before we go beyond this, let's say you and I am doing a business. So I put $100, you put $100. So together we have $200 in the middle. And then we are using that. So right now at given point, you have $200, I have $200. But let's say I'm a little bit greedy and I'm taking that dollar towards me a little bit, like I'm utilizing them a little bit more. Just imagine this. Not that I took the whole $200, then our relationship break. I'm not talking about that break. I'm talking about at a given point of time, I'm just using it a little bit. So I can say this, that at a given point of time, as I have $200 more, like the $200 towards me a little bit more, I am slightly rich. And obviously you will be that time slightly poor. Same thing happened with this electron. We call them bond pair electron or bond electrons. So when there are 2 atoms, those who attract their electron differently, not in case of carbon, hydrogen, but there are some atoms such as oxygen, such as nitrogen, they have electron affinity, meaning attraction towards the electron a little bit more than others. And what they do as a result of the fact, what they do, they attract the electron towards them a little bit more. Again, they didn't take the whole electron, because if you take, the bond breaks. We don't want that. We still have the sharing, but they're claiming the electron towards them a little bit more. And we know electrons are negatively charged. We can imagine that negatively charged cloud. So when the negatively charged cloud towards you, you become slightly negative. That's what happened to oxygen. That's what happened to nitrogen. They become slightly negative. And obviously the other person, in this case, let's say hydrogen, they become slightly positive. We denote those by delta negative and delta positive. I'll come right here, these slides. So right here, if the oxygen, okay, imagine there are 2 electrons here. That's a pair of electron here, pair of electron here. Ignore this. This is one water molecule, H2O. That's a water molecule, H2O. So this pair of electrons is attracted by oxygen. So they will gather a delta negative. They should have wrote delta negative here also. I got this picture from a Google image. So the hydrogen become delta positive. Same thing, this hydrogen become delta positive, so they become delta negative as well. Here, this picture will be slightly better. You see that oxygen has two delta negative, one here, one here. So oxygen can have two delta negative because they are getting this electron from two bonds, and hydrogen become delta positive. This, we call them polar covalent molecule because they create a pole, like North Pole, South Pole, they create a positive pole and a negative pole. So when oxygen attract those bond electron towards them a little bit, they become delta negative, and hydrogen become delta positive. So with two delta negative on their head, oxygen and hydrogen, each one has delta positive, they create a pole, positive pole and negative pole. This type of compound we call polar covalent compound. So water is an example of polar covalent compound. On the other hand, methane, CH4, is an example of non-polar covalent compound because hydrogen and carbon, they attract electron almost equal. So they don't have this problem. Now, when I said this problem means what happened because of the formation of that tiny charge, what they do, they attract their neighbors now. Because in a drop of water molecule, there could be like billions of water molecules. So the other H plus, which is positive, and the oxygen, which is delta negative, they will have a weak attraction. That's why they're denoted by dotted line. So look here, this oxygen and the neighboring hydrogen, they form a hydrogen bond. This same oxygen, because they have two delta negative, they form a hydrogen bond right there. So this weak attraction between the neighboring atom, we call it hydrogen bonds. So that's the third variety of bond. Now, why this is so significant? Because in a drop of water molecule, there will be tons, like billions of hydrogen bonds. So they kind of like interact, like it's like a social interactions. So they create a network of molecules. So water in a drop, they create a network molecule. This network of bonding, although weak, individually these bonds are much weaker than this covalent bond. Although weak, but billions of these bonding in a drop of water molecule change water property a lot. And that changes makes water is one of the most significant molecule in the life, including human life. That's why when scientists look for life, they look for water first. Because if there is water, most likely there is life. So water supports life. Your body, like 50 to 60% or 70% body weight is by water. So water chemistry becomes invaluably important because of this hydrogen bonding, what water changed their solvency, meaning how universal solvent they are. They can have like cohesion, they can have addition, they can have chemical reactivity, they can have thermal stability. So all these things makes water is an amazing molecule for life. So we need to know a little bit of water properties. This is exactly what I just said, that they form solution with many chemical inside the body. So they are chemically reactive. They moderate temperature, meaning their thermal stability there. So for example, the 1 gram of water, if you have an ideal condition, 1 gram of water, if you want to increase their temperature by 1 degree, so let's say 0 degree water, you want to make it 1 degree water, you need 1 calorie of energy. So for 1 gram of water, you want to increase their temperature by 1 degree, you need 1 calorie of energy. Using that same energy, if it had been another non-polar molecule, such as, let's say, nitrogen, it will increase 4 degrees. So water can be liquid for a very long time because they have a high heat specific heat capacity, and they can stay liquid for a very long time. Otherwise, think about outside temperature in the summer is 80 degrees Fahrenheit, and your blood will evaporate, so you'll die. Doesn't happen because water does not evaporate at the temperature that well. They evaporate slowly, but not that they're going to go 100% like any other, such as nitrogen. So that thermal stability are very helpful. Okay, and when you look for the plant, they're required for photosynthesis. That's an amazing property of water, which we are not interested right now. So water literally, because, and all of this because of hydrogen bond. And now I'm going to say another interesting property of water. Normally, if it is a liquid, if you take out the heat energy and the liquid slowly become solid. So this is the solid. If you heat them, become liquid. If you heat them, become gas. So if you take a liquid, if you take out heat, and then this slowly will become solid. So if you have water, if you take out heat, and this slowly will become ice. In normal case, like normal in other cases, such as iron, such as any other, iron is a good example to understand. If you're liquid iron, if you solidify them, they'll be very heavy. So because the molecules are going closer to each other. Remember in the beginning, we learned in the liquid, they're far apart, in the solid, they're closer together. So when they're going close together, they're heavier. But in case of water, at 4 degrees Celsius, so from 10 degree to 9 degree to 8 degree to 7, 6, 5, 4, once you reach 4, the water is most dense at that temperature. Because once you reach 3 degrees, the water is not getting denser because those hydrogen bonds, they need some space. Just imagine they keep guarding like this, so that, like, imagine everybody has an umbrella open. So that if you have an umbrella open, after a certain distance, let's say people are getting closer, 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 but after a certain distance, you can't get closer anymore because of that umbrella. Those hydrogen bonds, like an umbrella of the water. All the way bond, but they keep a distance between their neighboring molecules. That's why at 4 degree, water is the densest. 3 degree water is not as dense as 4 degree. That's why in the aquatic solution, in aquatic conditions, in the lake, what happened in the summer times is like this. Now the cold water comes, cold air comes, and the above temperature, which is like closer to the air, they're getting low. So they, let's say they become 7. Once a 7, they go down. Okay, once they become 6, 6 become heavy, go down. Once they become 4, 4 goes down. Now this 4 is the heaviest, they're densest. So once it becomes 3, they will be on top of 4. Once they become 2, they'll be top of 3. Once they become 0, the ice will form right here. So in the winter lakes, this is ice. This is all 4 degrees Celsius water. And that's why all the aquatic life can live there happily, even in the winter time. Okay. So that's, so anything about water is about their hydrogen bond. So hydrogen bond makes water is a very special molecule which supports many things, including, as I said, they serve as an universal solvent. So when you talk about solvent, we need to know about what is a solution that's coming up. But before we go to that, just to quickly mention 2 things about inorganic and inorganic. Organic compound. Organic compound is our next lecture. So there are many different type of definition. One easy definition is inorganic compound. They normally lack, their main primary compound is, main primary structure is not carbon and hydrogen atom. But again, carbon dioxide, for example, is the product that we produce, but it's still inorganic, okay? Although it has carbon. But usually, lack of their main structural component is not carbon, hydrogen. On the other hand, organic, their main structure is carbon and hydrogen. So when you talk about sugar, protein, and lipid, all these molecules later on, we're going to talk about mainly carbon and hydrogen structures. So always have covalent bond. But in this case, they may not have covalent bond. For example, sodium chloride is a salt that we produced before, like when sodium and chlorine form a bond. They are not organic molecules. They are inorganic molecules, because sodium and chlorine, when they create an ionic bond, they are created those kind of inorganic compound. So inorganic compound, mostly acid, bases, and salt, apart from water, carbon dioxide, and oxygen. Although the reason I separately mention them, because people sometimes think they are something to do with the living things, so they could be organic, but we categorize them inorganic because the carbon and hydrogen is not the primary component in that cases. Okay. So water creates a lot of solution. Um, as I said, it's a tremendous molecule and a very helpful molecule in the body. It's approximately 2/3 of your body weight. And solution of water is called aqueous solution. Aqua means water. Now, what is solution again? Solution, the definition is homogeneous mixture of two or more substances is called solution. This is the keyword, homogeneous mixture. That's the keyword. So when you mix two substances, say for example, you take a glass of water and you put 1 teaspoon sand and you stir it nicely, that's not a homogeneous solution. When you have a glass of water and a sand, it's not a homogeneous solution. The sand will seems everywhere, but if you keep it due to gravity, it's going to precipitate in like 5 minutes. So that means sand is separating from the water very easily. But when it's a homogeneous, let's say you put 1 teaspoon sugar in it and you stir it, that sugar is kind of like vanishes in the water. That's a homogeneous solution, meaning wherever you test, you will get the same taste. Same thing with the salt. It's not that you cannot separate them. You can, it takes a longer procedure. So homogeneous mixture cannot be easily separated. That's called solution. The solution has two things, solvent and solute. Solvent is the one that help the other one dispersed. And solute is the one that get dispersed into the solvent. So when you take a water and sugar, water is the solvent, sugar is the solute. But the example that I'm giving you, which is normally required for biology, is when solvent and sugar, this is like a solid liquid mixture. A homogeneous mixture or solution can be also the gas, can be solid, can be liquid. We don't want that detailed chemistry here. We just need to know a simple definition of solution and solvent, which is liquid, and a solute, in this case solid. So liquid, solid, solution, and all water solution, we call it aqueous solution. Water is an universal solvent, meaning it helps a lot of non-polar and polar molecules to get dissolves. Now, when it dissolves, it becomes a solution, you get it. But then we can see sometimes some solution is acidic, some solution is basic, some are neutral. Those are the words we use often, because we have to understand a little bit more body chemistry to understand the activity of the enzymes and all those things later on. So we need to know a simple definition of acid and bases. Okay, so what is an acid? Acid is a substance that donate H+ ion in solution, or H+ ion, meaning when hydrogen lose an electron, become H+, because they remember their atomic number is 1. So that become nothing but a proton. Hydrogen atom does not have neutron. Hydrogen atom has 1 electron, 1 proton. When they become H+ ion, meaning hydrogen ion, they already releases the electrons. So they have only 1 proton. That's why some book will define acid as acid is a substance that can donate proton in a solution. So proton and hydrogen ion, H+ ion, is identical. Okay, so acid is a substance that can donate H+ ion or hydrogen ion or proton in a solution. So HCl, hydrochloric acid, is an example. When you break them down, dissociate them, they produce H+ and Cl-. So they are giving H+ in a solution. That means it's an acid. So hydrochloric acid is an acid. So what is base? Exactly opposite. Bases are the proton acceptor, those who can accept proton. Normally when the base is in the solution, we call them alkali. So the solution is known as like an alkaline solution. Okay, so you should know the word alkali, A-L-K-A-L-I, alkali, or alkaline solution. So, because that is, say, for an example, sodium hydroxide. So what sodium hydroxide, when they dissociate, this should be also arrow on the backside because it can go back and forth. So sodium hydroxide, when they dissociate, they produce sodium ion and a hydroxyl ion. This hydroxyl ion, what they can do, they can combine with H plus and remove as an H2O. So they can combine with H plus, remove as an H2O. So we can call it as a base. Why? Because the definition is base is a substance, or alkali is a substance that can remove H plus from a solution. So if you have an acidic solution, let's say hydrochloric acid, and if you put a drop of sodium hydroxide, this hydroxyl ion will remove this H plus in the form of H2O. So that means this is a base. Okay. So the base or the alkali is someone that can remove proton from a solution. Okay. So that's simple definition. Now, when we talk about acid base in a solution, we know that we always discuss about something called pH. Okay. So pH is a scale. pH is a measuring scale for hydrogen ion. Okay, the definition of pH scale is the negative logarithm of hydrogen ion concentration is called pH. So what is pH? pH is negative logarithm, that's a logarithmic scale. So pH is negative logarithm of hydrogen ion concentration. That is known as pH. Okay, make sure you understand this is a small p, which is in mathematics called negative log, and this H stands for hydrogen ion. Okay, so whenever you write a P, make sure pH, you write a small p, lowercase p, and an uppercase h. The other pH has no meaning. Okay? Like uppercase P and uppercase H, pH could be abbreviation of phone number, such as. But this is pH is a negative logarithm of hydrogen ion concentration. As it is a logarithmic scale, it goes from let's say 0 to 14. So from 0 to 7, that's acids. So this is acid. So whenever pH is between 0 to 7, that's acid. Alkali, we call mainly alkali base because your book used this word commonly, but normally when you go to the solution, we call them alkaline solution or alkali. From more than 7 to 14 is alkali or bases. Okay, pH 7, exactly in the middle, is called neutral. So for example, pure water has pH 7. Pure water. Follow the word. Pure water, not just simply water. Water, sometimes most water that we drink is slightly acidic because carbon dioxide gets into the water and makes a slight acidic. But pure water has pH 7. Anything, two things you have to understand. Anything below 7 is acidic. Anything above 7 is alkaline. 7 is neutral. That's first thing. The second thing, very important, more you go towards 0, so from 7, if you go towards 0, more acidic it is. So stronger the acid when you go towards 7, stronger the alkali when you go towards 14. So one more time, below 7 is acidic, above 7 is alkaline. More you go towards 0, stronger the acid. More you go towards 14, stronger the alkali. So pH 4 and pH 5. pH 4 is stronger acid compared to pH 5. Now, how strong it is? 10 times stronger acid, because this is a logarithmic scale. So every number, individual number, is like a 10 times. So pH 5 and pH 3. pH 3 is a stronger acid. pH 5, pH 3. So pH 3 is a stronger acid. How strong it is? 100 times stronger, because pH 5 to pH 4, 10 times, pH 4 to pH 3, another 10 times. So 10 times 10, 100 times stronger. Same thing, pH 5 to pH 6 is a 10 times stronger alkali. We do not call them because below 7, we can call 10 times less acidic. Or pH 7 to pH 8 is 10 times stronger alkali. pH 8 to pH 9, another 10 times. So pH 7 to pH 9 will be 100 times stronger alkali, and so on. Our blood pH is approximately like plus minus, there's a range plus minus 7.4. So our blood, most body pH, like a blood plasma is one of them. Just think about, because stomach has a different, like mouth pH is neutral. We will talk about that probably later on. But stomach pH is, for example, pH 1.522. So it's very strong acid in your stomach. That's why when you sometimes have nausea and you vomit, you know that how strong that feel, because that's a lot of stomach acid. They have extremely corrosive activity. But anyway, so blood plasma pH approximately 7.4. So now think, if you drink some acidic, so I'll give an example. Let's say orange juice is very acidic. I think we have a slide here. Yes. So look at here. Lemon juice is like pH 2, or grapefruit juice is like pH 3. So it's acidic. So let's say you take a glass of grapefruit juice in the morning, okay? And then your 7.4 pH will be, because you're adding more acid, so 7.4 will go down to 7.3. So then you drank another glass of grapefruit juice because you loved it. So it becomes 7.2. And then you drank a third glass because again, you're loving it. So it becomes 7.1. And by the time you're done, because if your pH changed from 7.4 blood pH to 7.1 or 7, you are gone. So in other words, if you drink 3 glasses of orange juice or grapefruit juice, or even a Tropicana 3 glasses of orange juice, you die. But that doesn't happen. And the question is why? Because there are some molecules called buffer. So what happened is, as soon as you drink some acidic, your body uses those molecules called buffer that resist the change in the pH. So buffer is something that does not allow the change in the pH. So this is buffer systems of the body. What is buffer? So buffer stabilizes the pH of a solution by either removing or replacing hydrogen ion. So if you add more hydrogen ion, they will remove it. If you take away more hydrogen ion, they will add it. That's called buffer. So buffer is a blood pH is approximately 7.35 to 7.45. So they said plus minus 7.4. So there are different type of buffering systems. So this one I want you to know right now, called carbonic acid bicarbonate buffer system. So what they can do, they can maintain a pH steadily by either removing or adding hydrogen ions. So the definition can be is that buffer is a substance that can resist the change in pH. Okay. Finally, there are different type of chemical reactions we're going to discuss about, and 3 of them in biology is extremely important that you should know: decomposition, synthesis, and exchange. So simply defined as decomposition, like when like HCl broken down into H plus Cl minus, like AB broken down A plus B, decomposition. Simple explanation. Synthesis, A plus B, like sodium plus chlorine, sodium chloride. Synthesizing, hydrogen plus oxygen, water. You're synthesizing something, so you're making something. So that's synthesis. Exchange, obviously, this is an example. So the hydrochloric acid and sodium bicarbonate together, carbonic acid and sodium chloride, they exchange this. Okay, so these 3 are common reactions that we see in biology. And there are a couple of additional terminology. For example, all the chemical reaction, sum of all the reactions in your body is called metabolism. They're divided into 2 groups: catabolic reaction and anabolic reaction. Catabolic reaction, when you break them, and generally they are exergonic, meaning they releases heat. And anabolic, when you put them together, making new, and generally they takes up energy. Generally they takes up energy, called endergonic, because they take more energy. Okay. So catabolic reaction, anabolic reaction. Together we call metabolism. So metabolism is a sum of all the reactions together, divided into 2 halves: catabolic reaction and anabolic reaction. And that is it. That is for the first chapter of the chemistry. So when you study this chapter, make sure you know matter, different states of matter, and then obviously what is elements, what is compounds, what is atoms, what is molecules, symbol of the elements. Again, do not have to memorize them, just read them once. Then a little bit detail of atom, like atomic structure. We are focusing only on the solar system model and the nucleus and the electronic shell. Then, proton, electron, neutron, and you need to know about atomic number. You need to know about mass number, isotopes. Okay? And I mentioned a couple of uses of isotopes. Read that from your book as well. And then we talked about bonding. So we talk about ionic bond, chemical, covalent bond, and hydrogen bond. Obviously, you should know all three of them very detailed. Then a little bit properties of water, because of the hydrogen bond, water has a tremendous different type of property, as I discussed, like solvency property. They have cohesion, meaning they can join together, make like a bubble. Addition, they can stick to the container. So for example, if you take a glass of water, if you drain them, you can make it dry, because your glass is not dry, because some water molecule is sticking to the glass. And then that is good, because that has a utilization in the body, because body, the serous membrane, they're covering your heart and the lung. They can utilize that cohesion and addition technology to make it accommodate. When the lung increases, the pleural membrane also goes up by that. Okay, then comes the chemical reactivity, then thermal stability. All these things, because of the hydrogen bonds, make water as a great candidate for supporting life. And then we talked about solution, and then acid, base. So any solution, make sure you know solution, solvent, and solute, acid, base, pH, buffer, and then chemical reactions. Okay, that's it for this chapter. Thank you.